Welcome to our deep dive into linear modeling in economics. Today, we'll explore how linear models help economists make sense of complex relationships in the real world. Whether you're a student, professional, or just curious, understanding these models is essential for interpreting economic trends and making informed decisions. Linear models provide a simplified way to analyze how one variable affects another, such as how income influences spending or how prices impact demand. Throughout this video, we'll break down the basics, walk through practical examples, and show you why linear modeling is a cornerstone of economic analysis. Let's get started by understanding what a linear model really is. Linear model is a mathematical equation that describes a straight-line relationship between two or more variables. In economics, this often means expressing how a change in one factor, like price, leads to predictable change in another, such as quantity demanded. The most basic form is y equals a plus bx, where y is the dependent variable, x is the independent variable, a is the intercept, and b is the slope. This simple structure allows economists to make predictions and analyze trends with clarity. By assuming a linear relationship, we can use data to estimate the impact of changes and guide policy or business decisions. Linear models are popular in economics because they are straightforward and easy to interpret. They allow us to quickly see how variables are related and to make predictions about future outcomes. For example, if we know how much consumer spending increases with each dollar of income, we can forecast economic growth. Linear models also serve as a foundation for more complex analyses. Even when relationships are not perfectly linear, starting with a linear model helps us understand the basic dynamics before moving on to more advanced techniques. Let's break down the linear equation y equals a plus bx. Here, y is what we want to predict, like consumer spending. X is the factor we think influences it, such as income. The value is the starting point or intercept, showing what y would be if we're 0. The b value is the slope, telling us how much y changes for each unit increase in x. This equation is the backbone of linear modeling in economics, making it possible to quantify relationships and test economic theories with real data. One of the most common uses of linear models in economics is the demand curve. This curve shows how the quantity of a good demanded changes as its price changes. Typically, the relationship is negative. As price goes up, demand goes down. By fitting a linear model to real sales data, economists can estimate how sensitive consumers are to price changes. This information helps businesses set prices and governments design effective policy. Linear demand curves are a practical tool for understanding markets. Just as with demand, linear models are used to represent supply curves. The supply curve shows how much of a good producers are willing to sell at different prices. Usually, as price increases, so does the quantity supplied. By applying a linear model, economists can estimate how responsive producers are to price changes. This helps in forecasting market outcomes and understanding how changes in costs or technology might shift supply. Linear supply models are essential for analyzing how markets reach equilibrium. Use a linear model, we need to estimate its parameters, the intercept and slope. This is usually done using statistical methods like ordinary least squares (OLS). By fitting the model to observed data, we find the line that best represents the relationship between variables. The estimated parameters tell us the strength and direction of the relationship. Accurate estimation is crucial for making reliable predictions and drawing valid conclusions from economic data. Slope in a linear model is a key indicator of how much the dependent variable changes in response to the independent variable. For example, if the slope is 0.5, then for every 1 unit increase in x, y increases by 0.5 units. In economics, this could mean that every extra dollar of income leads to 50 cents more in spending. Understanding the slope helps economists and policymakers gauge the impact of changes and make informed decisions. Intercept in a linear model represents the value of the dependent variable when the independent variable is 0. While this may not always have a practical meaning, since zero income, for example, is rare, it provides a baseline for the model. The intercept helps anchor the line and ensures that the model fits the data as closely as possible. In some cases, the intercept can reveal important insights, such as fixed costs in a cost function. Linear models rely on several key assumptions. First, the relationship between variables must be linear. Second, the errors or differences between observed and predicted values should be randomly distributed. Third, the variance of errors should be constant across all levels of the independent variable. Finally, the variables should not be perfectly correlated with each other. These assumptions ensure that the model's estimates are unbiased and reliable. Violating them can lead to misleading results. After building a linear model, it's important to check how well it fits the data. This is often done using measures like R-squared, which indicates the proportion of variation in the dependent variable explained by the model. A higher R-squared means a better fit. Economists also look at residual plots to spot patterns that might suggest problems with the model. Good model fit is essential for making accurate predictions and drawing meaningful conclusions. While linear models are powerful, they have limitations. Not all economic relationships are truly linear. Sometimes the effect of one variable on another changes at different levels, requiring more complex models. Linear models can also be sensitive to outliers, extreme values that can distort results. It's important to recognize these limitations and use linear models as a starting point, not the final word in economic analysis. Economists often use multiple linear regression to analyze situations where more than one factor influences the outcome. For example, both income and education might affect consumer spending. In this case, the model includes multiple independent variables. This allows for a more nuanced understanding of how different factors interact and contribute to economic outcomes. Multiple regression is a powerful extension of the basic linear model. Multiple linear regression, each independent variable has its own coefficient, showing its unique effect on the dependent variable. For example, the coefficient for income tells us how much spending increases with each extra dollar earned, holding education constant. This helps economists isolate the impact of each factor and avoid confounding effects. Careful interpretation of coefficients is key to drawing valid conclusions from the model. Sometimes, economists want to include qualitative factors in their models, like gender or region. These are represented using dummy variables, variables that take the value 0 or 1. For example, a dummy variable for urban areas might be 1 for city residents and 0 for others. Including dummy variables allows linear models to account for differences between groups and improve the accuracy of prediction. Interaction terms are used in linear models to capture situations where the effect of one variable depends on another. For example, the impact of education on income might be different for men and women. By including an interaction term, economists can model these more complex relationships and gain deeper insights into economic behavior. Interaction terms make linear models more flexible and realistic. Linear models are also used to analyze time series data collected over time. For example, economists might model how GDP changes year by year. Time series linear models can identify trends, seasonal patterns, and the impact of specific events. This helps policymakers and businesses anticipate future developments and plan accordingly. Time series analysis is a vital part of economic forecasting. Cross-sectional linear models examine data collected at a single point in time across different individuals or groups. For example, economists might analyze how spending varies across households in a given year. This approach helps identify differences between groups and understand the factors driving economic behavior. Cross-sectional analysis is widely used in labor economics, consumer research, and policy evaluation. Panel data combines time series and cross-sectional data, tracking the same individuals or groups over time. Linear models for panel data allow economists to control for unobserved differences between subjects and analyze how changes unfold. This approach provides richer insights and helps address issues like omitted variable bias. Panel data models are increasingly important in modern economic research. One of the main uses of linear models is to predict future economic outcomes. For example, businesses use linear models to forecast sales based on advertising spending, while governments predict tax revenues from changes in income. Accurate predictions help organizations plan budgets, allocate resources, and set strategies. Linear models provide a transparent and systematic way to make these forecasts. Linear models are invaluable for policy analysis. Economists use them to estimate the effects of policy changes, such as tax cuts or subsidies, on economic outcomes. By quantifying these effects, policymakers can weigh the costs and benefits of different options and make evidence-based decisions. Linear modeling brings clarity and rigor to the policymaking process. Businesses rely on linear models for a variety of applications, from pricing strategies to inventory management. For instance, a retailer might use a linear model to predict how sales respond to price changes or advertising campaigns. These insights help businesses optimize operations, maximize profits, and stay competitive in dynamic markets. Linear modeling is a practical tool for everyday business decisions. Understanding consumer behavior is a key goal in economics, and linear models play a central role. By analyzing how factors like income, prices, and advertising affect purchasing decisions, economists can predict trends and design effective marketing strategies. Linear models help businesses and policymakers understand what drives consumer choices and how to influence them. Linear models are widely used to study labor markets. Economists analyze how wages are affected by education, experience, and other factors. By modeling these relationships, they can identify wage gaps, forecast employment trends, and evaluate the impact of policies like minimum wage laws. Linear modeling provides a clear framework for understanding the dynamics of the labor market. Cost functions describe how a firm's costs change with output. Linear models are often used to estimate these relationships, helping businesses understand their cost structure and make production decisions. For example, a linear cost function might show that each additional unit produced increases total cost by a fixed amount. This information is vital for pricing, budgeting, and profit planning. Revenue functions model how a firm's revenue changes with sales volume or price. Linear models make it easy to estimate the impact of selling more units or raising prices. This helps businesses set sales targets, plan marketing campaigns, and evaluate the potential returns from different strategies. Linear revenue models are a staple of business economics. By combining linear cost and revenue functions, economists can model profit and identify the output level that maximizes it. This is a fundamental concept in microeconomics. Linear models make it straightforward to calculate the profit-maximizing quantity and price, guiding firms toward optimal decisions. Profit maximization is at the heart of business strategy. Elasticity measures how responsive one variable is to changes in another. Linear models are often used to estimate price elasticity of demand or supply. For example, a linear demand model can show how much quantity demanded falls when price rises by 1 unit. Understanding elasticity helps businesses and policymakers anticipate the effects of price changes and design effective interventions. Linear models are a go-to tool for forecasting in economics. By analyzing historical data, economists can predict future trends in sales, employment, GDP, and more. Forecasts based on linear models are used by businesses, governments, and investors to make strategic decisions. The simplicity and transparency of linear models make them especially valuable for communicating forecasts to a wide audience. Not all economic relationships are linear. Sometimes the effect of one variable on another changes at different levels. For example, the impact of advertising on sales might increase at first but then level off. In such cases, economists use nonlinear models or transform variables to better capture the relationship. Recognizing when linear models are insufficient is crucial for accurate analysis. Outliers, data points that are far from the rest, can have a big impact on linear models. They can distort parameter estimates and lead to misleading conclusions. Economists use diagnostic tools to detect outliers and decide whether to exclude them or use robust estimation methods. Handling outliers carefully ensures that linear models provide reliable results. Multicollinearity occurs when independent variables in a linear model are highly correlated. This can make it difficult to estimate the unique effect of each variable and lead to unstable parameter estimates. Economists use techniques like variance inflation factors, VIF, to detect multicollinearity and may drop or combine variables to address the problem. Managing multicollinearity is important for model accuracy. Heteroscedasticity means that the variance of errors in a linear model changes across levels of the independent variable. This violates one of the key assumptions of linear modeling and can lead to inefficient estimates. Economists use tests like the Bruch-Pagan test to detect heteroscedasticity and may use weighted least squares or transform variables to correct it. Addressing heteroscedasticity improves model reliability. In time series data, autocorrelation occurs when errors are correlated across time periods. This can bias parameter estimates and affect forecasts. Economists use tests like the Durbin-Watson statistic to detect autocorrelation and may use specialized models such as autoregressive models to address it. Managing autocorrelation is essential for accurate time series analysis. Choosing the right linear model involves balancing simplicity and accuracy. Economists use criteria like the Ackic Information Criterion, AIC, or Bayesian Information Criterion, BIC, to compare models. These criteria penalize unnecessary complexity and help select the model that best fits the data without overfitting. Careful model selection leads to better predictions and more robust conclusions. After selecting a model, it's important to validate its performance. Economists often split data into training and test sets, building the model on one and evaluating it on the other. This helps ensure that the model generalizes well to new data and isn't just fitting noise. Model validation is a key step in building trustworthy economic models. Economists use a variety of software tools to build and analyze linear models, including Excel, R, Python, and specialized econometrics packages. These tools make it easy to estimate parameters, check assumptions, and visualize results. Learning to use these tools is an important skill for anyone interested in economic analysis. Clear communication is essential when presenting the results of linear models. Economists use graphs, tables, and plain language to explain findings to policymakers, business leaders, and the public. Effective communication ensures that insights from linear modeling are understood and acted upon, making a real impact on economic decisions. Using linear models responsibly means being aware of ethical issues. Economists must ensure that models are not biased, that data is used appropriately, and that results are not misrepresented. Transparency about assumptions and limitations helps build trust and ensures that linear modeling serves the public good. Recent advances in computing power and data availability have made linear modeling more powerful than ever. Economists can now analyze massive datasets, build more sophisticated models, and test hypotheses with greater precision. These advances are opening up new frontiers in economic research and policy analysis. Let's look at a case study, modeling housing prices. Economists use linear models to analyze how factors like location, size, and interest rates affect home values. By fitting a linear model to housing data, they can predict prices, identify trends, and inform buyers, sellers, and policymakers. This practical application shows the real-world value of linear modeling in economics. In labor economics, linear models are used to study wage determination. By analyzing data on education, experience, and industry, economists can estimate how each factor contributes to wages. This helps identify wage gaps, inform policy, and guide career decisions. Linear modeling provides a clear, evidence-based approach to understanding labor markets. Linear models are also used to analyze international trade. Economists model how factors like tariffs, exchange rates, and economic growth affect trade flows between countries. These models help policymakers design trade agreements, assess the impact of policy changes, and promote economic development. Linear modeling is a key tool for understanding the global economy. The future of linear modeling in economics is bright. As data becomes more abundant and computing tools more powerful, linear models will continue to evolve. Economists are developing new techniques to address complex relationships and improve prediction accuracy. Linear modeling will remain a foundational tool for economic analysis, helping us understand and shape the world around us. Wrap up: linear modeling is a fundamental technique in economics, offering a clear and systematic way to analyze relationships, make predictions, and inform decisions. While it has limitations, its simplicity and power make it indispensable for students, professionals, and policymakers alike. By understanding the basics of linear modeling, you're better equipped to interpret economic data and contribute to meaningful discussions about the economy. Thanks for joining us on this journey through linear modeling in economics.